All right, well, we might get started. So good afternoon, everyone. I'm Kate Bongiovanni, and I'm a climate science master's student and science communication enthusiast. And it's my great pleasure to welcome you to this science festival event hosted by the newly merged School of Geography, Earth and Atmospheric Sciences. I'd like to begin by acknowledging that those of us in Australia are meeting on the unceded lands of various Indigenous peoples. I acknowledge the Wurundjeri people, the traditional custodians of the land on which I'm coming to you, and I extend that acknowledgement to the people of the lands which you are coming to us on, recognising connection to land, waterways and sky above. I also pay my respects to Aboriginal elders past and present who may be joining us today. Before we start, and to promote a sense of community in this online format, I encourage you all to say hi to all panellists and attendees by using the chat function. So you could tell us where you're joining from today as well. When you do that, please make sure to select panelists and attendees so that everyone can read your message. Winston Churchill famously said, "The further you can look back, the further forward you are likely to see." Last week's IPCC assessment report told us that our atmosphere and climate are changing faster than at any other time in human history. In addition, the report emphasised the importance of putting recent and future warming in the context of past climate changes, from the Holocene to the Pliocene and beyond. But what is it we can learn from the past to help us face the challenges ahead? Today's seminar brings together 3 researchers from the School of Geography, Earth and Atmospheric Sciences who explore our weather and climate of the past in different ways and on very different scales. From dusty manuscripts to fish ear bones to next generation climate models, Drs. Lyndon Ashcroft, Amy Prendergast and Joe Brown are helping us look further back so we can see further forward. Lyndon, Amy and Joe will speak for about 10 minutes each, leaving plenty of time for your questions at the end of the session. So please feel free to submit questions at any time via the Q&A function at the bottom of your screen, and we'll come to them at the end. I'd like to now hand over to our first speaker. Dr. Lyndon Ashcroft is a lecturer in climate science and science communication here at the University of Melbourne. Her research uses the past to help us prepare for the future, exploring Australian climate using historical documents and weather observations. Lyndon communicates science regularly on community radio. She edits a peer-reviewed journal on scientific data, and her writing was selected for the 2019 Best Australian Science Writing Anthology. She was a 2019 to 2020 Science and Technology Australia Superstar of STEM and received the 2020 Australian Meteorological and Oceanographic Society Science Outreach Award. Thank you, Lyndon.
Thank you so much, Kate, for that lovely introduction, and not just because I am your supervisor that you said such lovely things. Thank you very much. Let me just share my screen. Hopefully I can do this. And hopefully you guys can see that okay. This image is the gates of the Adelaide Zoo in South Australia in about 1883. If you look behind the gates there, if you squint a bit, you should be able to see an elephant with somebody riding the elephant, very different to the zoos that we see today. And I wanted to start with this picture because I wanted to tell you a little story about a heat wave that occurred in Adelaide in 1897. It was the end of 1897. It was from Boxing Day until about the 30th of December. The weather records that we have for the time say that the observations were the temperatures during the day were above 40 degrees for every day during that heat wave, which is a pretty significant record even by today's standards. The nights were also really warm, and according to the 29th of December, I think it was, the overnight temperature didn't drop below 31 degrees. The overnight temperature, which is pretty crazy. According to the newspapers at the time, at least 65 people died from this heat wave, and many children suffered severely from heat stress and had to be brought around by wet cloths on their face and ice on their body. Now, in this zoo, there were also casualties. There was a rare drill monkey, which is related to the mandrill, who passed away. They also lost both of the seals in the zoo, and many animals, many birds died as well. The zookeeper at the time, Mr. Minchin, I'll just read from the newspaper here, said that he'd never seen the carnivores in such a state of distress. They will not eat anything and are reduced to a state of weakness which is pitiful to observe. On Thursday, he placed bags in front of various cages and houses, and the caretakers spent all day hosing down the enclosures to keep the temperatures down. Now, why am I telling you this story? What can we learn from this horrific event, this terrible heat wave? What we can tell from this is that information about the past provides really rich detail about extreme events that occurred. This heat wave and the instrumental and documentary data that we can get from it tells us that heat waves are a part of Australia's history. In fact, this particular heat wave is used by some loud people on the internet to suggest that climate change isn't happening, although in this talk, I'm sadly going to tell you that that's not the case. What's also interesting about this event, even though it was significant, even though we have some numbers about it, it doesn't appear in the Bureau's official record. This graph here on the left shows the average mean temperature in Australia every year from 1910 through to 2020. And you can see there, not only have we got a really significant warming trend, but that the observations begin in 1910. And that's because it is this time, and from this time into the present, where we've got enough weather stations around the country to give us an accurate and fairly confident picture of what's going on year to year in our climate. This is our network here on the right of 112 reference temperature observation stations that are used to capture Australia's climate and Australia's temperature variability. So if the Bureau is only starting their information and starting their record, when we say the hottest on record or the driest on record, this is the record that we're talking about. My career as a historical climatologist, looking for observations before that time and trying to understand events that have happened before the modern record, does that mean that it's a waste? Does that mean that there's nothing we can explore about older instrumental and documentary information? No. The field of historical climatology has been a large area of research in the Northern Hemisphere for a long period of time. But in the Southern Hemisphere, it hasn't really been around that long. We've only been really spinning up and ramping up our understanding of historical climate variability in Australia for the last 15, 20 years or so. And there are a lot of observations that exist before this time, including these observations that exist in Adelaide and plenty of others that can tell us a lot about the climate of our past. Now, you're all here because you're interested in the climate of the past, but just to clarify why it's so important that we understand our weather events in the longer context, we really need to know about historical weather observations and extreme events, not just on the daily scale or the weekly scale like a heat wave, but previous droughts and sort of decade to decade variability. So we can get a greater picture of risk, so we can understand how Australia's highly variable climate has behaved in the past to get a baseline level of how it might change in the future. This image here comes from a pretty severe drought in South Australia in the 1860s. We also need historical instrumental weather observations and documentary accounts to connect the modern period and the kind of recent past with the work that Amy and Joe are going to talk about, the longer period where we have natural records of our climate variability. And to be able to tie those two things together, we need as long a record as possible of numerical weather observations. And finally, for Australia, we actually just need some representation. This map here shows you the number of weather stations that are used to develop a global picture of climate variability in 1788. The red dots show stations there, and you can see that there's not that many around the world, right? We've got one, Sydney. William Dawes took weather observations for the first 3 years of colonial invasion at Sydney Harbour. But if we go to 1860, we've got a lot more observations in the Northern Hemisphere, but we really don't have anything in the Southern Hemisphere still. We've only got one station in the central, northern Victoria, southern New South Wales. So we need more observations. We need more historical weather observations across Australia, across the Southern Hemisphere, to improve our understanding of what's happened in our country, what's happened in our hemisphere, and improve the accuracy of what we see from the global picture of climate variability. We can do a lot better than this one dot. And one place in Australia where we can add a dot to this map is Adelaide. Now, Adelaide's a really interesting place. Those of you who know a bit about Australia's colonial history, you know, Adelaide is famous and proud of the fact that it's not a colonial settlement. It was a free settlement. And people from Adelaide maybe have a slight accent that you can pick up. But from a meteorological point of view, they've also got some really great weather data. Observations begin in Adelaide in 1838. There was an amateur meteorologist there, William Wyatt, who took records for about 6 years, and politician and surveyor George Kingston took observations of rainfall for a really long time, from 1839 up until 1879, which means there's a continuous daily record of rainfall for Adelaide, pretty much from settlement to the present. Adelaide's also famous because, thanks to Charles Todd, who was the surveyor and he was the meteorologist of the colony, and he was also the astronomist, he was just an all-round overachiever. He took observations at the observatory in Adelaide. This is an image on the right here from the early 1900s. He organised observations to be taken in 2 different types of thermometer sheds, 2 different houses where a thermometer could be kept every day for about 40 years. And having these parallel observations occurring at the same time means that we can connect modern observations, which were taken in the Stevenson screen, which is that white box on the left of the image, with observations that were taken earlier in what's known as a glacier stand or a Greenwich screen, which is the screen on the right there that the person is observing from. So Adelaide's got heaps of data, and we've been working with these observations for a long time. We've known about a few of them, but some have been recently uncovered, like this one here. It's a beautiful, look at this beautiful handwriting. These are weather observations that were recently uncovered from the Survey Office in Adelaide from the 1840s and 1850s. And they're really detailed records, 3 times a day, allowing us to really understand what the weather was like, what the synoptic systems were like over 160 years ago. On most days, not on Sundays. People took a break on Sundays, and sometimes they took a break on Saturdays as well, like this particular day where there was a holiday in honour of Captain Sturt's departure on his exploring expedition. But the person taking notes couldn't help themselves and still said that the weather was quite fine. So these observations, we can extract them from these historical documents and check them for quality. We can cross-reference the information that we have from the numerical data with documentary accounts of what was going on in newspapers and archives and remarks that are provided in these meteorological journals. And then we can splice them together and get a picture, the longer picture, extend that record back in time to see what the climate and the weather was like. So what can we see? Looking first at rainfall, this is from work that was done, we did a couple of years ago. These 3 curves here tell you about the total amount of rain on the top. And in the middle, we're looking at the wettest rain day of each year. And the bottom curve there is telling you the number of rain days each year from 1839 to 2017. Unlike the temperature curve, you're not seeing a clear trend there, but we can see lots of decade to decade variability. We also repeated this kind of analysis for Melbourne and Sydney. And what's interesting is that while for Adelaide, you can see the wettest day of the year occurred there, that big spike in the middle graph occurred in 1925, when there was a severe thunderstorm that dropped about 140 millimetres in 24 hours. For Melbourne and Sydney, the biggest spike in that particular graph, telling us about these extreme rainfall events that we really need to prepare for in the future, as many climate models predict that severe rainfall events will become heavier. But the historical record captures events that are stronger and more intense than the events kept in the Bureau of Meteorology's record. So these historical observations are allowing us to find extreme events that we can't see in the modern record. Unsurprisingly, we can also see that heat waves are becoming more frequent. As we know, they are a part of Australia's climate, and Adelaide is particularly prone to heat waves. But the historical data and the instrumental and documentary record together are both showing that heat waves are becoming more frequent. And there are lots of different ways we can use instrumental data and check them for quality. This result here uses one method to assess the data for quality, but if we use a different method, the results are still the same. This graph here is comparing the first graph I showed you in the black lines with another approach for analysing data quality. And they're both showing an increase in heat waves over time. Similarly, we're also seeing a decrease in cold extremes. This graph here is looking at really cold days assessed by a temperature threshold. But if we also look through the documentary records of snowfall events around Adelaide, like this picture here on the left from 1905, the number of snowfall events are also decreasing. Again, I mean, it's not surprising, but now we've got another 70 years of information to provide us with a longer term context. So what does this mean now? What can we do next? We're discovering more weather observations all the time that are giving us a better picture of our climate variability in Australia and really lighting up the whole southern hemisphere in terms of long-term variability. These observations that we're rescuing, they're not only contributing to studies of Australia's climate, but they're being sent to global data sets and global models, and they're improving how our country and how our hemisphere is being represented, which is just so valuable. The other thing we can do that with these historical events is get more accurate assessments of risk, of what might happen in the future. And a question that we're now able to ask, and this is a question that's been asked recently in the US. The bottom picture here on the right is from the big dust bowl droughts in the 1930s in the US, where some research is actually led by an Australian researcher, Tim Cowan. Instead of asking what are big droughts going to look like in the future, they asked, if that drought was to happen now, what would it look like? And so we can start asking these questions. If these big famous heat waves in the past, if they happened now, what would they look like? And this particular study in the US found that if the 1930s Dust Bowl drought occurred now, it would be it would involve an extra week of heat waves, and it would also be twice as likely to occur. So this kind of nuanced question is a slightly different way to examine and communicate the risks that we've got coming up and the risks that we can avoid if we act quickly, which I think is a really valuable tool scientifically and for getting the message across to people. I'm really looking forward to answering questions at the end of the session, and thanks so much for listening to me today. I'd now like to pass on to my lovely colleague, Dr. Amy Prendergast. Amy is a senior lecturer in the School of Geography, Earth and Atmospheric Sciences, and she's a DECRA Fellow. Amy works on a very different timescale. She does such amazing work looking at the relationships between humans and environmental change, from the thousands-year scale up to the millions of years scale, and I'm sure she's going to tell us all about that. So take it away, Amy.
Thanks. I'm just seeing how I go sharing my screen. New share. How's that looking? Can everyone see?
Looks good.
Cool. Okay, so we've just heard from Lyndon the really great amount of information we can learn from historical records of climate change, but now I'm going to describe how we can extend this knowledge further back in time to learn about past climate variability and responses to this variability from humans through the combined use of palaeoclimate proxies and archaeological records. So, in many regions of the world, historical and instrumental records may only extend back a few decades, and they rarely extend back beyond a few hundred years. So this is why we need to turn to the palaeoclimate record, where we can use climate proxies to extend our understanding of past climate variability back from decades to millions of years. So paleoclimatology is the study of past climates prior to the instrumental record. And we do this by analysing various proxies which are preserved in natural archives. So archives such as tree rings, corals, ice cores, and ocean sediments. And these proxies can be physical, chemical, or biological. So for example, the width of tree rings can give us information about past temperatures and rainfall. Chemical proxies such as oxygen-stable isotopes in tiny fossils preserved in ocean sediment cores can help us reconstruct temperature variability. So here's an example of where studying these tiny microfossils in ocean sediment cores has allowed scientists to understand long-term fluctuations in climate in our current geological period, the Quaternary, which covers roughly the last 2.5 million years. So all of these wiggles that you can see here in this diagram are fluctuations between cold and warm phases. So these are glacials and interglacials. And so during glacials, when it's cooler, ice sheets expand, as you can see here. And during interglacials, when it's warmer, ice sheets retreat. And so over the last million years or so, the cyclicity of these changes is roughly every 100,000 years. So the last glaciation, the last glacial maximum, when the ice sheet was at its maximum extent, occurred around 18,000 years ago. And the impact of these changes, oh, sorry, something just happened with my computer. Sorry, can people, my words just decided to restart right in the middle of my presentation. So I'm just going to try and reshare my screen. Sorry. Escape that. All right, apologies for that. Are we back? Can someone give me a thumbs up or a yes?
Yeah, all good.
Cool. All right. So yeah, the impact of these glacial and interglacial cycles, these changes, has important implications for the distribution of plant and animal species across the planet, which has implications for human survival. And so, for example, agriculture and sedentary lifestyles only really started in the last 11,000 years or so, when we entered a relatively stable interglacial phase of the climate. So why do we need paleoclimate records? So we know that these natural cycles of climate variability are longer than these historical and instrumental records. So paleoclimate records can provide a way to place the human-induced climate changes that the planet is currently experiencing within the context of natural climate variability. And so by studying paleoclimate records, it becomes really obvious that many of these changes that we're seeing at the moment are way beyond the range of natural variability. So for example, here we have this record of CO2 concentrations, and we see that from looking at gas bubbles preserved in ice cores, that we have over the last 800,000 years not really exceeded 300 ppm until the Industrial Revolution, and now we're up to beyond 415 ppm, so way beyond the range of natural variability. And this threshold of 300 ppm prior to the Industrial Revolution hadn't been exceeded while humans were around on the planet, Homo sapiens, that's us. So in my own research, I'm particularly interested in the intersection between paleoclimate reconstruction and archaeology to understand human-environment interaction. So as I'm sure you're all aware, climate and environmental change affect the distribution of food and water across the planet, changing the availability of shelter, rising and falling sea levels expose and cover tracts of land, and climate and environmental change also affects the physiological tolerances of organisms. All of this affects the resources that we rely on to survive. But humans aren't simple creatures at the whim of Mother Nature. We have complex adaptive responses, which include migration and dispersal across the planet to find the resources we need, shifts in technology to deal with environmental changes, shifts in subsistence, so what we eat, and we can eat a wide variety of things, and other shifts in behaviour as well. But there's been many studies that have looked at the intersection between environmental records and human-environment interaction. But what many of these studies have in common is sometimes the environmental records that they use are distant from the archaeological sites from which we understand human behaviour, and they're often at quite low resolution, so decadal or millennial. And these records don't necessarily reflect the changes that happened locally where people were living. Humans respond to the climate around them and the environment around them at local and seasonal scales. And so if we want to understand the effect of past climate and environment change on human behaviour, we need local and seasonal records. And the best place to get these is from or very close to the archaeological sites that we're studying. In the case of my research, a lot of it involves analysing biogenic carbonates such as mollusk shells. So this research falls under the umbrella of sclerochronology, which is the study of physical and chemical variations in the accretionary hard tissues of organisms. And it's pretty much analogous to dendrochronology, but instead of studying tree rings, we're looking at the carbonates, which are deposited incrementally on these shells or corals or otoliths. And this growth in chemistry is modulated by the environment. And so by analysing this growth in chemistry, we can get high resolution snapshots of environmental change at annual to tidal resolution, so super high resolution records. So many organisms with incremental hard parts are preserved in archaeological sites, and they're often the remains of ancient meals. So things such as mollusk shells, bivalves and gastropods, otoliths or fish ear bones and teeth from animals that have been hunted by the ancient inhabitants. And so these archives and their associated proxies can provide environmental information across marine, freshwater and terrestrial realms. And because they're the remains of ancient meals, the environmental records we get from these can be directly linked to human activity. And so an example I'd like to share with you today, linking palaeoclimate records from archaeological sites to try and understand why, at around 40,000 years ago, modern humans were expanding across the world, and yet our closely related archaic humans, Neanderthals, became extinct, despite many similarities in the two species. So for those unfamiliar with Neanderthals, here are a few little facts. So they were around in Eurasia from about 400,000 to 40,000 years ago. They're a bit shorter and stockier than us, potentially adaptations to living in a cold climate. And they survived a series of glaciations over this time, yet they became extinct around 40,000 years ago. But we had many similarities. So we both had very big brains. We both had the ability for language and some aspects of culture. So we wore clothes, we made art, we had jewelry, we probably all buried our dead in some way, so that we had this kind of cultural, symbolic thought processes. And we were so similar that we in fact even interbred with one another. And so most people alive today have a small percentage of Neanderthal DNA in their genome. So why did modern humans survive and Neanderthals disappear? There are many theories, which I don't have time to go into today, but the one that I do want to look at is climate change. So one of the main places where modern humans and Neanderthals interacted and interbred was in the Levant, in the far eastern Mediterranean. And so this was a particularly interesting place to be over the last 100,000 years ago or so. So this is a place where modern humans and Neanderthals interbred. Modern humans made their way through here to Europe, whereas Neanderthals came kind of from Europe into here. And so this is a region where they interacted. During this time, the climate was experiencing a rapid shift known as Dansgaard-Oeschger and also Heinrich events. So seen here in the Greenland ice core as shifts between cooler and warmer conditions. These shifts occurred within decades, so within the lifetimes of individuals. And so anybody alive at the time, be they Neanderthal or modern human, would have had to have adapted to these changes, which may have also led to changes in seasonality and resource availability. And so anybody, Neanderthal or modern human, would have had to have adapted to these changes. And one of the fundamental questions is, were modern humans better adapted to deal with these rapid climate changes than Neanderthals? In order to understand this, we need a detailed understanding of these rapid climate change events, as well as a link to archaeological records from where we understand behavioural change. And so I'm taking you to a few sites in the Levant here where I'm looking at reconstructing this using mollusk shells from various archaeological sites. One of these sites is Ksiakil in Lebanon, where I've reconstructed subseasonal resolution sea surface temperatures from archaeological mollusk shells covering the time when modern humans and Neanderthals were coexisting. So here's a summary of some of our results from the sites, and these are the only graphs I'm going to show you in the presentation, I promise. So the box plot shows a summary of all of our data through all the layers of the site, moving from the youngest Epipaleolithic to the oldest initial Upper Paleolithic. Don't worry about these terms. But then we're going to take a closer look at individual shells from which we can reconstruct seasonality data. So each of these graphs shows a high resolution sequence from an individual shell over several years of growth. And in the layers dated to cooler periods, Heinrich events and stadials, we see generally cooler mean sea surface temperatures and a higher range of seasonality, so the difference between summer and winter temperatures. During warmer interstadial phases, we see warmer mean sea surface temperatures and a generally reduced range of seasonality. And this pattern is repeated throughout the sequence. What this pattern tells us is that human occupation occurred not only in varied temperature, but also in varied seasonal regimes. And the people occupying this region would have had to have dealt with these changes in resource timing and availability. So what does this mean in terms of human-environment interaction? We know that these environments in which modern humans and Neanderthals were living were subject to rapid environmental changes, and in particular, rapid changes in seasonality. This fluctuating seasonality would have led to unpredictable swings in resource availability in the landscape. Rapid environmental change and changing seasonality would have made resources uncertain, forcing populations to adapt. So why did we survive these changes and Neanderthals didn't? From our perspective as Homo sapiens, it's really tempting to say we triumphed because we were superior. But if we go back tens or even hundreds of thousands of years ago, this seems to be far from the case. Neanderthals were smart, they had big brains, they had sturdy bodies, they were stronger than us. Yet modern humans were somehow resilient. This is perhaps due to subtle differences in their behaviours and culture. So we know that modern humans at this time had really broad subsistence strategies. They had diverse toolkits which would have allowed them to deal with these environmental changes. And they also ate a large variety of different things, from small mammals to plants to large mammals and shellfish. They also lived in larger and more connected groups. So this we know from both archaeological and genetic evidence, and they seem to have broad exchange networks, evidenced, for example, by the occurrence of similar technologies at broad sites across the landscape. Neanderthals, on the other hand, seem to have slightly less varied diets, focusing on larger game species, although this wasn't always the case, and their tool assemblages were not as diverse, as they tended to live in smaller groups. Neanderthal population density was probably already low at this time due to a combination of factors, including environmental change and perhaps disease and natural disaster. And this probably allowed the population to be swamped by modern human immigrants who were more adaptable and resilient to these rapid climate changes that were occurring. So I'm just going to finish by saying that humans have dealt with rapid climate changes throughout history and prehistory in a variety of ways. And so we can use this combination of the archaeological and the paleoenvironmental record to study what worked, what didn't work, what allowed us to become resilient to adapt to climate changes and what didn't. And some of the keys to adaptability we can find when looking at the archaeological record are broad societal connections, reduced inequality, broad use of resources, so not over-reliance on a few key resources, as well as having friendly neighbours and trade relationships. And so I'll finish there. I just want to pass on to our final speaker now, Jo Brown. So Dr. Jo Brown is a lecturer in paleoclimate modelling. Her research uses climate models to investigate both past and future climate variability, with a focus on monsoons, El Niño Southern Oscillation, and climate of the Australian and Pacific region.
Thanks, Amy. I'll just share my screen now and wait till that comes up. Okay, so I'm going to use my 12 minutes or so to tell you very briefly about the way in which we can use global climate models to look back to the past and learn something about what may lie in the future. These figures down the bottom here show climate model simulations for the last glacial maximum for the mid-Holocene, around 6,000 years ago, and for a future under a high emissions greenhouse gas scenario. So there's a lot of interest at the moment in the idea of past warm climates as future analogues or case studies for what possible futures may hold. And this figure here from a paper that came out last year summarizes this quite nicely. So they have the temperature shown in this colored line here, going back from the present day to the left, back to 100 million years ago. And you can see a number of different snapshots within that period of different past climates. And down below, the grey shaded line shows the atmospheric CO2 concentrations that corresponded to these past climates. So you can see we find ourselves at a relatively cool and low CO2 part of this 100 million years. If we look to the right-hand side, they also include possible future scenarios known here as SSPs. And there's a low, medium and high emissions scenarios shown. And you can see that under the low emissions scenario, which will be approximately what we might aim for to meet the Paris Agreement targets, we end up with warming levels that are similar to that seen in the Pliocene here. So this Pliocene period is the focus of a lot of attention as the recent climate analogue that may represent our future if we're able to follow a low emissions pathway. And I'll focus on the Pliocene for most of this presentation. So how do we actually go about modelling past climate with a climate model? Well, we actually use the exact same computer climate models that are used in the IPCC report to look at future climate. Of course, these models are mainly developed to look at current and future climate, but they can actually be used quite effectively to simulate past climates. We just need to change some of the inputs into the model. So for example, we change what's called orbital parameters, basically the configuration of the Earth's orbit. We change the greenhouse gas concentrations. We change the height and the extent of ice sheets and other important boundary conditions. And then we can run the model to simulate a wide range of past climates. And examples that have been simulated include the last glacial maximum around 21,000 years ago, the last interglacial, which is around 125 to 130,000 years ago, the time when we were last at the warming levels that we are currently at the moment, and then the mid-Pliocene around 3 million years ago, which is, as I said, an analogue for a slightly warmer future. So I want to talk a bit more about the mid-Pliocene. If we go back in time through this figure shows about the last 7 million years, and there's this little warm bump here reconstructed from marine sediment records, which is identified as this mid-Pliocene warm period. So it's about 3 to 3.3 million years ago. And at this time, reconstructions indicate CO2 levels were around 400 ppm. So you might already recognize that we've already exceeded that value. And the temperatures were around 2 to 3 degrees warmer than our current climate. It's also worth noting that the sea level was very much higher at this time, up to 25 meters higher than modern sea level. And this was due to the smaller polar ice sheets. In particular, there was no permanent northern hemisphere ice sheets at this time. And that obviously should send some flashing red warning signs that a temperature warming of only 2 to 3 degrees could be associated with this very large increase in sea level. So there's been a lot of effort to reconstruct Pliocene climate from different proxies and also to model mid-Pliocene climate. This is a summary of vegetation reconstructions from a lot of different lake records and marine records around the world. And when we have pollen in these records, we can actually reconstruct the kinds of vegetation that was growing in the past and therefore infer what the temperature and rainfall were like as well. And so to cut a long story short, this figure or this study found that these subtropical regions, which lie just poleward of the tropics between about 25 and 35 degrees north and south, were relatively wet during the Pliocene, whereas today these regions are quite dry. Most of Australia lies within this subtropical kind of climate zone and has a relatively dry climate. So the Pliocene, the mid-Pliocene vegetation indicates it was actually wetter. This is also supported by some work from colleagues in our school. Cal Snyderman and John Woodhead and others have got a large number of speleotherms or cave deposits from sites across the Nullarbor in Western Australia here. And they look at the growth rate of these speleotherms to find out about the amount of available moisture in the past. And so in the mid-Pliocene, they had a very high speleotherm growth rate, indicating a lot of available moisture. And they've also looked at fossil pollen trapped in the speleotherms to reconstruct the vegetation. And this agrees. They find indications of quite lush forested vegetation, where today we have primarily grasslands and quite dry vegetation. So they also agree that it was quite a lot wetter at this time in the Southern Hemisphere subtropics. But if we look at projections for the future, looking at output from all the climate models that are run and input into the IPCC reports, they generally show in the future a drying, in particular if we focus in here on Southern Hemisphere winter, June, July, August. Across this Southern Hemisphere subtropical band, it actually becomes quite a lot drier, whereas the tropics are becoming wetter. And so this pattern has been described as a wet gets wetter, dry gets drier pattern. So this has made a lot of people scratch their heads and ask, how can we reconcile the information about the Pliocene as a warmer climate which was wetter in the subtropics, whereas the future projections indicate a warmer climate which is drier in the subtropics. And so we turn to climate models to try and understand what's going on. And this study that came out a few years ago, they simulated an idealized future warmer climate where they have 4 times CO2, so it's quite high. And then we have a Pliocene simulation, which is meant to match the reconstructed sea surface temperatures from all those different ocean sediment records. And so in the future simulation, in general, the tropics become quite a lot warmer than the present day. These are the warming relative to pre-industrial. Whereas in the Pliocene case, there's actually very little warming across the tropics, whereas there's quite a lot of warming in the subtropics and mid-latitudes and high latitudes. And so these two climates have quite different gradients in temperature between the equator and the mid-latitude regions. And this turns out to be important. So if we look at the rainfall changes in our idealized future climate, there's a lot of increased rainfall across the tropics in the convergence zone and monsoon regions, whereas there's drying in the subtropics. Whereas in the Pliocene case, it actually becomes wetter in the subtropics, and in large parts of the tropics, it becomes drier. So there's quite a big difference, and this is associated with different transport of moisture because of that temperature gradient pattern. So first thing that the Pliocene can tell us is it's not just a simple question of is it warmer or is it cooler? It's actually about which region's warm and what are the temperature gradients. And so we find that in future simulations, the tropics get warmer and wetter, the subtropics get drier. These little cartoons down the bottom, don't worry about the details, but basically the future climate is a kind of wet gets wetter, dry gets drier. But the Pliocene, the tropics didn't warm, the subtropics warmed and became wetter. And so we have a dry gets wetter and wet gets drier, the opposite response. The second part of the story is the fact that the Pliocene climate was actually a stable equilibrium climate. It was basically long-term equilibrium with the CO2 concentrations. Whereas when we look at our future climate models, we're actually looking at a climate where it's getting warmer every year because the CO2 levels are rising year on year. And so we thought a more fair comparison would actually be to look at future stabilized climates. And this is a paper that came out a couple of years ago now in Nature Climate Change, where we made use of some extended model runs that ran out to 2300 and stabilize the CO2 levels and the temperatures. And I haven't really got time to go into too much detail here, but basically when we have the global warming transient climate, this southern hemisphere winter rainfall declines. But as the temperatures stabilise, and in this case it happens a bit later in these high emissions runs around this point, as it stabilises, the rainfall actually begins to return because the temperature gradient is actually reversing. So we basically conclude that there's a big difference between equilibrium and transient climates. So that's my second key lesson, I guess, is a rapidly warming transient climate is not the same as an equilibrium. So the Pliocene was definitely an equilibrium, but the transient climate of the near future will have quite different temperature gradients, partly because the Southern Ocean in particular warms more slowly and takes time to catch up to the tropics. So the takeaway here is that the mid-Pliocene is a good analogue for a stabilised warmer future, such as we might hope to achieve under the Paris Agreement, but it's not a very good analogue for the next few decades if we continue to warm. And so I just wanted to finish off by kind of stepping back and thinking about where we're headed. So if we were able to stabilise our greenhouse gas concentrations near current levels, and I just put here the value from a couple of days ago, around 415, we may reach a mid-Pliocene-like climate. Although it's important to note that the sea level will continue to rise for many thousands of years in response to that warmer climate. But if we allow the greenhouse gas concentrations to continue to rise, instead of being here in the Pliocene, we may actually approach much warmer climates such as the early Eocene or other more extreme past climates. And that would be very, very far out of the comfort zone of the entire human race. So I will leave it there.
Many thanks to Joe, Lyndon and Amy for those fascinating talks. We've got, if anyone's got any questions, if you'd like to put them into the Q&A, we'll go from there. Otherwise, I'll start off. And I guess one thing I was wondering was, you've talked about some paleoclimate data and also early instrumental data. But how do these actually get incorporated into the IPCC report?
I can briefly comment on that. So it's actually quite exciting that in the most recent IPCC report, they actually use paleoclimate information interwoven into the whole report, whereas in the last one, there was just a single paleo chapter. And I think this time around, there's a lot more awareness of the way that paleo information can provide a baseline. So for example, the temperatures are now described as the warmest since the last interglacial, 125,000 years ago. And the CO2 levels, unfortunately, are now described as the highest since the Pliocene. So there's that really long view putting in context, because of course we need to look back such a long way now to find relevant examples from past climate.
Cool. Thank you, Joe. I think it's a really important point to note that how paleoclimate data is now incorporated throughout the whole IPCC report.
Yeah, I can also add for the early instrumental data, I've seen from iteration and iteration of the IPCC report that the value of these early observations is becoming increased. There's still a lot that we don't know, and we still have to be really careful when we use these observations. We can't just trust the data implicitly. We have to understand how the observations have been taken and any biases that they may have. But as we find more and more records, then we can be more confident in what we're saying. And I think that's being appreciated in every iteration of the IPCC report.
Awesome, thank you. So we've got another question in the Q&A, one for Amy. Question is from Runjia, and they're wondering, what's the spatial scale of human migration under the seasonality of climate change?
Yeah, I mean, I guess that's really dependent on the region and the kind of geographic constraints of human migration. And I guess when we think about human migration too, we might not necessarily think about it as single event in, you know, in a person's lifetime that they just undertake once. It might be something that happens iteratively. So as environments change, as resource pressure gets too much, people might expand, you know, the geographic region that they use. So yeah, it's really kind of dependent on the particular local circumstances of a population living in a region.
Thank you, Amy. So I think you three have provided us with like the paleoclimate and also the early human story and the historical documentary data, but a story that's missing here is from the Indigenous knowledge. So I'm just wondering, what role can Indigenous knowledge play in linking past climate changes to present and future change?
I can answer that a little bit. Like, I think particularly in terms of Australia, like the Indigenous knowledge of cultural burning in terms of managing country is really important. And it's something that, say, for example, the research of Michael Sean Fletcher is getting at through looking at the paleo record and seeing how long these landscapes have been managed through cultural burning. And then we see nowadays what happens when that management of country is taken away, and the kind of extremes of the bushfires and things that we've seen over the last few years. And so I think kind of linking that kind of Indigenous knowledge with the paleo record can really, I guess, strengthen that management of landscape and country.
Thanks, Amy. And I think mentioning extremes again there, I think this links into another question that we've got in the Q&A from Jeff, asking about extreme heatwave frequency. So I think, Lyndon, this is a question for you. Did an earlier slide show less extreme heatwave frequency, even though heatwave frequency increased? And if so, what might this mean?
Yeah, so one of the slides that I showed, let me just see if I can find it again. Here we go. This graph here on the right is showing the number of heat waves in Adelaide from 1838 through to the end of 2019. It doesn't have 2020, 2021. And it shows the number of heat waves that are occurring. And then we had an extreme heat wave where a heat wave had to be really long and include some really warm days and some really warm nights. And these events, I think the takeaway from this graph isn't that they are decreasing. I'm not seeing a decreasing trend there, but it is to show that these really intense events that can be devastating have long been a part of Australia's climate and Adelaide's climate. So the nature of where Adelaide sits in southern Australia as well, we get influenced by these great big blocking high pressure systems that just allow heat to build and build and build, and so that it sticks around for a long period of time. That's been a feature of our climate for a while, and I think these results show that is still the case. I will also say that this is one definition of heat waves, and it's one station as well. There are lots of other studies that have used different definitions and larger networks of observations and models as well, and have found that the number of heat waves is obviously increasing in frequency and intensity, whether you define that by how long a heat wave is or how hot a heat wave is. So yeah, this result was a little bit interesting, but I wouldn't say it's overly controversial.
Thanks, Lyndon. I think we might just have time for one more question. So I guess with Amy, you touched on how past humans have had to adapt to rapid climate changes. So how can we kind of translate this to the present and to like current technologies and social arrangements, and what kind of techniques can we use now to adapt to current change?
Yeah, that's a big question. So I mean, I think looking at the role of technology, obviously technology has a huge role to play into like a clean energy transition, but there's also a danger that's particularly happening in Australia of seeing technology as this kind of solution to stop action on climate change. So that's kind of one point that's a big discussion. But then in terms of looking at social arrangements, like what we can learn from the archaeological record is often that societies that have greater inequality or that have like a socio-political system that is less adaptable, they're the societies that will tend to not survive rapid climate changes, and also societies that are reliant on particular resources, so a very small variety of resources, and they perhaps don't have trade relationships with other populations in order to be able to maintain their lifestyles if environment rapidly changes. And so I think, you know, it's kind of in line with adapting our societies to have safety nets, to reduce inequality, and to be friendly with our neighbours. That's what's going to help us survive.
Thank you. Lyndon or Joe, did you have anything to add on to that?
I don't think anything that will be based on my own research, only my own positivity and determination for the species.
Okay. Well, I'll just ask one more question to Joe then from the chat from Craig. In your long-range stabilized RCP 8.5 simulation, had ocean aspects such as the Northern Hemisphere ice cap and Southern Hemisphere sea surface temperatures stabilized as well?
Yeah, so the ocean has gone some way towards reaching equilibrium, but there's no fully dynamic ice caps in these models at the moment. So it's still kind of the next stage in developing models that can actually represent the full sort of ice age cycles with dynamic ice sheets. So when we talk about that in the paper, we say near equilibrium because it hasn't reached a full complete equilibrium.
Cool, thank you. So I think that brings us to the end of our seminar today. So thank you to everyone for tuning in. Just like to note that as well as forming part of the University Science Festival events, today's webinar is part of a seminar series from the School of Geography, Earth and Atmospheric Sciences. So next week's seminar will be held on Tuesday from 1 to 2 p.m. and will be given by Professor Andy Tompkins from Monash University on the topic of meteorites, messengers from Mars, and from our nascent solar system 4.5 billion years ago. You can find all the details via the link that should be in the chat now. And I'd just like to say one more thank you again to all our panelists, and thank you and enjoy the rest of your National Science Week.